Hi there, everyone. Here's section 3.6, derivatives as rates of change. So this is one of our first exposures to, a very applied, applications of derivatives, essentially. So suppose we have position. Okay, so position is often represented with an s. So s equals some function of t, where t is typically time in this application. Then velocity is the first derivative of position, f prime of t, or ds dt, depending on what type of notation you're using. The magnitude of velocity is speed. Okay, so velocity has magnitude and direction, whereas speed just has magnitude. So usually if you have a positive velocity, that indicates forward motion. If you have a negative velocity, that indicates backward motion. And then acceleration is the first derivative of velocity and the second derivative of position. Okay? So let's see an example with these. Okay, so here, this is from section 3.6 in the book. A feather is dropped on the moon. So on the moon, a feather will fall to the ground at the same rate as a heavy stone. Suppose a feather is dropped from a height of 40 meters above the surface of the moon. Then its height above the ground is given by s equal to 40 minus 0.8 t squared. So from that, we want to determine the velocity and acceleration of the feather the moment it strikes the surface of the moon. Okay, so, whoops, let me change the color here. Okay, so here's our position function, and it's a function of time. Okay, so time is changing, position is changing based on time. Okay, so as time goes on, the height is going to be less than 40. That's why we're subtracting off a 0.8 t squared. So the first thing I'm going to do is I'm just going to compute v of t and a of t, and then I will solve for what I need to solve for. So v of t is the first derivative of s of t, so that would give us a minus 1.6 t. Okay, the derivative of 40 is 0, and then the derivative of this second term here, I'll need to use the power rule. Okay, acceleration is the derivative of velocity, which just gives us negative 0.16. Okay, so there are my three functions: position, velocity, and acceleration. Okay, so we're asked to determine the velocity and acceleration when the feather strikes the surface of the moon. So the feather is going to strike the surface of the moon when its height is 0. Okay, now we're told that the height, or position, is given by s. So we want to know, when does s of t equal to 0? Once we solve that equation for t, we use that t to plug into our v of t and our a of t. Alright? So let's solve that. So we've got 40 minus 0.8 t squared equals 0. So we have 40 equals 0.8 t squared. I'm going to go up here. So we've got t squared is equal to, 40 divided by 0.8 is 50. And then we square root to get t is equal to plus or minus root 50. Now, we've got two roots here, so let's think practically about this. If we assume that we drop the feather starting at t equal to 0, then the feather is going to strike the moon at some positive time after 0, and so we just have t equals positive root 50. Okay, we can neglect the negative root because we're assuming t is time, and negative time in this context doesn't make sense. Okay, so now we can compute the velocity at time root 50. So the velocity at this time, the time when the feather is striking the ground, is going to equal negative 1.6 times root 50. Okay? And the acceleration at this given time Well, there's no dependence on t, so it just equals negative 1.6. And those are our answers, okay? This is the type of answer I would expect on an exam. If you noticed from the first exam, I'm not really expecting you to even have a calculator. I write the exams, and I don't use a calculator when I take the exams myself. So, if you want a calculator, great. If you don't want a calculator, you should be totally fine. If you want to multiply this out, I'm sure it would give you some decimal value, but we've illustrated that we know the calculus at this point. Okay. Other things to note, the acceleration is constant, so it's a constant acceleration similar to the acceleration due to gravity here on Earth. Okay, we're not pushing the feather at all, we just dropped it, we just released it, and so that's a constant acceleration that occurs. The velocity we see is negative, and this makes sense because we have a falling object. Okay, let's see another example. Okay, so average and marginal cost. So this is a very specific application again of derivatives. So we have a cost function, c of x, I'll underline that. C of x is equal to 1,000 plus 0.1x, and x is ranging from 0 to 5,000. Okay, so we have some item, and we want to find the average cost and the marginal cost functions. So there's a very specific definition for average cost and marginal cost in this section. We're told that average cost is equal to your cost function divided by x, and marginal cost is the derivative of the cost function. Okay, so that's just how it's defined in the book. So for part A, okay, we find c of x over x. So the average cost, your book represents it as a c bar. So that's equal to 1,000 plus 0.1x divided by x, which is 1,000 over x plus 0.1. Okay, so there is our average cost function. Our marginal cost function, I'm going to call it c prime of x, is equal to the derivative of the cost function, which just ends up being 0.1. Okay, so here we've got average cost and marginal cost. Okay, part B is asking us to determine the average and marginal cost at x equal to a. Okay, so for this problem, a is 2,000. So this is simply asking us to evaluate the two functions we found in part A at x equal to 2,000. So for part B, I'll just squeeze it up here. The average cost when x is 2,000 is going to equal 1,000 over 2,000 plus 0.1. So that's a half plus 0.1. That equals 0.6. Okay, sort of squeezing things in here. C prime of 2,000, well, it has no dependence on x. It's a constant 0.1. Okay, so the average cost when you have 2,000 units is 0.6. The marginal cost is 0.1. Okay, so part C asks us to interpret the values obtained in part B, and average cost per item when 2,000 items are produced is 60 cents per item. That's the meaning of what we have found right here. Okay. Whereas marginal cost tells us the cost of producing the 2,001st item. So here the 2,001st item would cost 10 cents. Okay, so that means probably things are getting cheaper the more that you make. It costs you less to make them. That's kind of what I would infer from this. Alright, well, that's all I've got for section 3.6. have fun exploring some of the different application problems with that, and I'll be checking in with you.